Great. Thank you for having me here. And I just want to say up front, please feel free to ask questions during the talk, just interrupt. Very informal. I don't know if you can raise hands here on WebEx or not, but no need for that. So, yeah, we'll just have a discussion here. So, I'm going to talk today about the AdS CFT correspondence for scalar field theory and lattice AdS2 and AdS3. And it's based on these two papers down here, done with Rich and collaborators, mostly at BU. Okay, so first, as always, let's begin with the motivations for why we want to do this. So I guess it should be pretty easy to see that we want to explore the AdS-CFT correspondence, and we want to do so non-perturbatively. So we really want to be able to study the phenomena of strongly coupled systems. Whoops. There we go. Moreover, maybe you've heard of CFTs or conformal field theories, but they're very special types of theories that are important for understanding quantum field theories and other physical systems, at special points, but nonetheless, they're very nice to study, and we have a lot of analytic control over them. And the AdS-CFT part of this comes from the fact that the AdS-CFT gives us many tractable examples if using an effective theory in AdS. So what I mean by that is if you take anti-de Sitter space or AdS and you throw a theory in there that you can basically, the boundary always has a conformal symmetry in the AdS-CFT. So when you throw in a bulk theory and you tune the parameters of the theory in AdS, you're actually scanning over, you're changing the putative conformal field theory on the boundary. So you're able to scan over by tuning the bulk parameters. You're able to scan over a large class of CFTs on the boundary. So that's what I mean by that. Yeah, and normally
So,
to be tracked.
Cameron, just to be annoying, how many people on this call know what a conformal field theory is, or any definition of it?
Well, I have explicitly not done equations. I'm sure people have heard of conformal field theories, which are
Well, that's what I'm
simply,
asking. I'm asking the rest of the group.
well, they'll have to respond then, Rich.
Okay.
So, and I will also, this is just the motivation page. I will go over a slide on conformal field theories, etc., like that. So to be tractable, the bulk theory is usually taken to be perturbative, meaning, we do some sort of perturbation theory in the bulk so we can calculate results. Of course, to go beyond this, to study potentially real physical systems, we need numerics, right? And that's where kind of performing lattice calculations in this space is important. So the goal of this talk and this research is to potentially learn about new kinds of CFTs. That's the overarching motivation for why we're going to do this. So the outline of today's talk is as follows. First, I'm going to explain what AdS is, anti-de Sitter space is, and how you go about tiling or tessellating it or tiling it or latticizing it. Then I'm going to do the two-dimensional case. It's called the hyperbolic disk. I'm just going to check some perturbative calculations. That's all I mean by Witten diagram perturbation theory. We're then going to move up a dimension into three-dimensional AdS space. And we're going to do, at that point, some Monte Carlo calculations and then calculate some finite volume critical scaling exponents. Well, not quite, but I'll explain when we get there. And then I'll close, of course, with future possibilities and directions. All right, so the first part, let's talk about AdS and how to tile it. So when I talk about AdS in this talk, or anti-de Sitter space, okay, I'm talking about Euclidean anti-de Sitter space. And famously, Euclidean anti-de Sitter space is just the same as hyperbolic space. And this slide is probably the most mathematical slide of this talk, but it is important to just set out the definitions at first. You can reference back here afterwards. But to construct anti-de Sitter space, how we do that mathematically is we take the hyperboloid here in flat Minkowski space with the following metric. And it has a nice property that we can write this metric like this. So we can split hyperbolic space in d+1 dimensions. We can write the metric into a time component and then a hyperbolic space in one less dimension. And of course, there are various coordinate systems. So, when we're talking about hyperbolic space, the manifold remains unchanged, meaning the space itself remains unchanged. It's just this space. But of course, we can put different coordinate systems on it, depending on what our system is that we're studying. And particularly, since we're interested in studying things on the boundaries, that's where CFTs live or QFTs, we're going to be interested in what the boundary geometry is. So if you look into this literature, you'll find there are mostly three, I mean, there are more, but three mostly used coordinate systems. There's the Poincare coordinate system, and on its boundary, you just have a circle in 2 dimensions or a generalized sphere in d dimensions. There's also the so-called global coordinate system here, which is just, instead of a sphere, it's just a cylinder, or the generalization of the cylinder. That's all this means by r cross SD minus 1 here on the boundary. There's also the upper half plane coordinate system, which just means on the boundary, it's just flat space. Okay. So how should we tile AdS, this negatively curved space? Well, I think it's useful and intuitive to think about the cases that we know. So I'm going to first talk a little bit about flat space and then also a positively curved space. But generally, we want a lattice prescription to maintain as many of the symmetries of the original space as possible. So in flat space, the first thing that probably comes to mind to most of us here is just a normal square lattice or just a normal triangular lattice, something like this, okay? And we see that in both these cases, of course, we're trying to mimic flat continuous space, but they both have their own discrete symmetry group. So on the left here, the square lattice has translation invariance, and so does the honeycomb lattice. They're realized as a Z4 or Z6 symmetry in mathematical speak. It's also important to realize that because we're in flat space, there is no inherent length scale, okay? So we can zoom in or zoom out of the lattice, so to speak. So we can make the squares or triangles any size, really. And also, because the space is non-compact, we have an infinite number, right? So flat space, we can go off to infinity. So if we theoretically want to tile all of flat space, we have to have an infinite number of squares or triangles here. Okay, so in comparison, how do we do this for the sphere, S2? So in positively curved space, and Rich will talk about this later today in much more detail, but in positively curved space, like the sphere, the icosahedron is actually the best you can do. When I say the best you can do, I mean that all the triangles here are equilateral triangles, right? We want all the triangles to be, we want a regular, uniform tessellation of the object we're trying to study, right? So that just means, in fancy words, we want all the triangles here to be equilateral, all the same. So, right, for the sphere, the icosahedron is the best you can do. An important difference also is that now there is an inherent length scale, right? There is the radius of the sphere that you're trying to discretize. And the size of the triangles now are inherently related to the length of this radius. The space is also compact, right? It's not an infinite space. It's not a non-compact space. It's a compact space. So the interesting thing about H2 here, which is the hyperbolic plane or two-dimensional AdS, is that it's kind of the flat space and the positively curved space together a little bit. Okay, so if we go back here, just looking at the sphere, I said this is the best you can do. We're bringing 5 triangles together at a point. I say it's the best you can do because a cruder approximation of the sphere is just maybe the the tetrahedron, for example, which has, and then there's, I guess, the octahedron, which might have four triangles come together at a point. So the best here is 5 at a point. And then in flat space, when we were dealing with triangular lattice, we had 6 equilateral triangles meet at a vertex. So perhaps unsurprisingly, for a constant negatively curved space, such as this AdS, two-dimensional AdS space that we're trying to tessellate, 7 is the minimum number of equilateral triangles that we can bring together at a vertex. So here's a somewhat stylized picture of that. And from these equilateral triangles, we can basically just tessellate outwards and we can create our lattice that way. So from these equilateral triangles, we can create a lattice of the space. Yes, and I should mention here that this is somewhat of an optical illusion. Basically, AdS space, this infinite, constantly negatively curved space, has been projected down onto a unit disk here. So it looks like the triangles are getting smaller as you go out, but really, in the actual space, they're all equilateral triangles. So I said this in words, but I'll point it out here on the slide here that the space now, it's non-compact, kind of like flat space, but unlike flat space, but like the sphere, it has an inherent length scale, the AdS radius, right? And that's basically, you can think of, it's hard to visualize the negatively curved space. If you can plot it on Mathematica or wherever, and you think of it as just a hyperboloid for the two-dimensional case, but it's just, you know, how much curvature this hyperboloid has, it has an inherent length scale assigned to it, right? And that's what's called the AdS radius here. Okay. So it's important to note briefly that there is a mathematical structure behind this tiling. We're not just saying, let's just put equilateral triangles on and tile the space willy-nilly. Like, you can actually think of this, mathematically speaking, as a group, and it's called the triangle group. And this triangle group maintains a maximal discrete subgroup of the AdS2 isometries. And all that means, that's fancy speak for saying that it is the best discrete realization you can make of AdS2 that best preserves, the character of that space. Okay? So central to our tessellation will be this so-called 2, 3, 7 triangle here, which is this red triangle down here. And basically, what the triangle group does is it takes this fundamental unit triangle here, and then the generators of this group, just fancy word, meaning you can act, the group has some action on the space, and what this action does in this case is it just simply takes this red triangle and it flips it and rotates it around to create these larger equilateral triangles, which themselves you can think of as being flipped and rotated around to create the lattice. So you can actually mathematically generate the lattice from this triangle group, layer by layer, right? So the generators of the group, the action is on this space is they simply they make this lattice, they tile the space, which is actually pretty neat. And this capital L equals 3 down here, all that means, just to explain the notation, is that we call this a 3-layer lattice, meaning like this is the first layer, out here is the second layer, and then finally at the end here is this third layer. All right. So before I start to talk more about, actually the physics here and doing things, I guess, are there any questions maybe on this introductory section on how to tile or tessellate anti-de Sitter space?
Hi, I have a question. So
Sure.
you mentioned in the last slide that you can tessellate the full space by using the group operations.
Yep.
So thinking about maybe crystallographic lattices, the Bravais lattices, is this an instance of a Bravais lattice, or you can't do that?
That's a good question. It's not, I don't think, an instance of a Bravais lattice, but you can think of it, how you construct one of those lattices is very similar. So yes, you can think of the construction as being the same, as that you can just act by the generators of the group, construct the lattice, and you have your lattice basically.
Okay, thank you.
Yep. Okay, so if there aren't any other questions, I'll move on to the two-dimensional case, which we did down here in this paper. Okay, so the two-dimensional case is also known as the Poincare disk model. Okay, the Poincare disk model of the hyperbolic plane, it's described by this metric here. All I want to point out here is that, let me just get a picture up here as well, is that you see right here, you have basically the metric for a circle here, and then you have some funny factor out front. And all that says is that as you get to the boundary in this case, right, so we're tiling an infinite space, anti-de Sitter space, and now, you know, in this coordinate system, the boundary at infinity here is now at r equals 1, at this unit radius here, right? So you see we have obviously rotational symmetry. We basically just have the metric of a disk with this funny, it's called the Weil factor in fancy speak, but this funny factor out front. And we see that as r approaches 1 here, this term blows up, you know, and that's where infinity is. Okay, and that also maybe explains why there's this kind of warping of the triangles as you know, in this picture at least, as you get towards the boundary here. So this is the metric we're going to use. This is the picture you should have in the back of your head here, that the boundary is at r equals 1, and we're going to, you know, as we tile the space, the triangles are going to get closer and closer to this boundary, but they're never going to get quite there. So what are the properties of this lattice? So one of the properties is the number of vertices increases exponentially in the number of layers. So what I mean by this is the number of points on the boundary is exponential in how many layers out you are. The consequence of this is that most of the points, you know, are on the boundary. And so, I mean, it's if you know, I don't want to talk too much about AdS CFT, but you know, in terms of this correspondence, it's kind of an interesting, it kind of hits you in the face in the sense that, you know, you might wonder how can, you know, I'm thinking with a 30,000 foot viewpoint here, you might think if there's this correspondence between the bulk and the boundary, how can the boundary encompass like all the points, you know, in the bulk? Well, actually, when you discretize it here, you see immediately that most of the points are actually on the boundary. And, you know, you might have remembered in one of the previous slides, I was taking 7 triangles and putting them together at a point, and that's what, you know, made a uniform equilateral triangle lattice and hyperbolic space. And so in this case, when you take 7 triangles together at a point, it actually works out exactly that the number of points on the boundary is the inverse of the golden ratio, so about 61%. Now, one of the things I failed to mention is that you could actually bring 8 triangles together, or 9 triangles, or 10, or infinitely, you know, you could just keep iterating up from there together in hyperbolic space. And when you increase the number of triangles you bring together at a point, you find that the number of points on the boundary actually becomes, it approaches asymptotically the total number of points in the bulk. So, you know, it's kind of, you can really see in this discrete case maybe the intuition behind this AdS CFT correspondence. Okay, that was an aside. For our lattice here, of course, we deal with, whenever we introduce finite spacing, we have some UV and IR effects that we need to take care of. And so the UV cutoff in this case is from the finite lattice spacing, A in this case, that's just the distance, that's just the length of the equilateral triangles, you know, the distance between the points. And we have an IR cutoff, of course, from the finite volume of the lattice, meaning that we're never getting out here to r equals 1. And we can characterize these, you know, we can say, oh, the lattice gets within epsilon of the, you know, of r equals 1, and we can, we have control over these things, but I just want to point out that we have the usual UV and IR things to worry about. Okay. So now that we have our lattice, we understand some of its properties, what are we going to do? Well, we're going to study 5-4 theory at first. And what we're going to do is to study it, we need to discretize its action. Okay, so this is scalar 5-4 theory. This is the action for it in the bulk. To discretize it, excuse me, when we discretize it, we introduce finite differences. We introduce, finite spacing. These Kij here are known as the kinetic weights, which I'll in the next slide explain what these are geometrically. But I just want to point out that the actual thing, that we put on the computer, as we always do, we introduce some dimensionless parameters, and we can turn the action into this nice form here. And this is the one that we're going to put in the computer in, C or C++ or Fortran or whatever, where we can put in finite differences and have discrete points. It is kind of interesting to just understand geometrically what some of these, some of these terms are back here in the discretized action. So the metric, the square root g here, is just the area of the dual lattice heptagon, right? So if you take, so this is one layer, you have 7 triangles here. Of course, that's our lattice. There's a dual lattice. And that's described, one cell is described by this heptagon here. And so actually the square root g in this case is just the area of this dual lattice site. And the kinetic weight, so this coefficient in front of the derivative terms, this finite difference term here, this is just the ratio of the dual link, right, the side of this heptagon to the side of the equilateral triangle, right? So it's kind of, there's, again, more math on this page, but geometrically, it kind of makes intuitive sense what these objects are on the lattice. Okay, so now that we have an action, we want to actually compute some objects. We want to measure some observables, is what you might hear people say. So the one observable we're going to focus on is the bulk lattice Green's function. And we're going to focus on the bulk lattice Green's function because a lot of other observables can be computed from this. So if we take our action, since it's discrete, we can put it in sort of a, we can put it into this matrix-like form where M is just a matrix. Here, in this case, then the lattice Green's function satisfies this equation right here. So simply inverting the quadratic form here, this matrix, we can find the lattice Green's function like this, right? So if we write the action like this, the bulk Green's function is simply found by just inverting this quadratic form or matrix in this case. Okay, so comparing this to the continuum equation, here's the continuum lattice Green's function. So people can solve this equation in general AdS space, right? This looks pretty nasty, but it does have an exact analytic solution. So let me just explain what this is here. So the exact analytic solution we're going to be comparing this to is an exponential term. Okay, sigma here, this is just the geodesic, this is just the distance between 2 points, right? So if you take a point like at the center of the lattice and you take another point farther away, sigma is the geodesic between those 2 points, between the point x and x prime. This can be any coordinate system, which is why I've used x and x prime, but really in the back of our minds, we're using this Poincare coordinate system, but this is a general equation. So we have an exponential factor here, and then we have what's known as a, in the colloquial terms, a 2f1, meaning it's just a hypergeometric function, a regular one. And this thing takes in 4 parameters like this, But basically, all you need to know is that the bulk-Green's function is essentially this first exponential factor for all the values that we care about for delta, where delta is just related to the mass of, a particle or object we're going to study by this formula here. Okay? Yeah, so this is a small detail down here that just justifies why this term here is essentially 1 over all the ranges that we're going to look at. But needless to say, the bulk-Green's function is just this exponential term. All right, so good. So we kind of trudged through a bunch of math on slides here, which is not the most fun thing to do. But now that we know what we are trying to compare it to, namely this thing, what do we find? So let's first look at the lattice bulk propagator. I'm taking the massless case here, and I'm taking a L equals 7 lattice, so pretty large lattice. This Q equals 7, I avoided talking about this, but this really just means I'm taking, again, still 7 triangles around a single point instead of 8 or 9 or 10 or whatever. And I'm just going to look at the all-to-all propagator for all the bulk points. So we have our lattice on the disk, and I'm just saying literally calculate the propagator from one point to the other point, one point to the other point, all to all. So there's quite a bit of points in there, a bit of redundancy because the lattice actually has a 7-fold symmetry, but that's okay. Small detail aside. So if you do that, we expect to find when we look at the log of this object here, right? So if we take the log of this should just turn into a line with slope delta. Again, for the massless case, if m is equal to 0, since little d, we're in the 2D case, but little d in this case is 1, we expect then the slope here to be 1 to make this 0. And what do we find? We find exactly that. We find the fit is basically 1. Okay? And this is with, yeah. So we find the fit is basically 1. Now, in this slide, I've ignored, I say bulk points, so I've ignored the points on the boundary, the true outer points, because those true outer points, well, they're on the boundary. You have to worry about boundary effects on a lattice, and so normally you'd create a bunch of points and maybe make your measurements close to the center or far away from the boundary because you don't want to worry about boundary effects, But even if we just naively, and again, also most of the points in this case are on the boundary. So you might expect that, you have most of the points on the boundary. It introduces all these boundary effects. It can kind of screw things up, But when you just naively include all the points now, so there are many more points now, and you just fit it, you still get a somewhat reasonable answer, 1.04 in this case. Okay? So just kind of a caveman computation. You don't really need to worry about the boundary. All right. So something slightly more complicated. Now we can look at the boundary propagator. So let's just go ahead and take only the propagator from boundary point to other boundary point. And why we want to do this is going back to the motivation, we're interested in studying CFTs or QFTs more generally on the boundary, and the CFT actually has a very well-known form for its propagator from boundary point to boundary point. It should be something like this. So this is a more non-trivial check, and also it might be a little more difficult because this boundary, as you can see, is a little the projection makes it more so, but it's obviously ragged, and this discussion on the previous slide about boundary effects. But even if you just look at the boundary propagator, in this case, still for the massless case, we have a very good agreement between the lattice and the analytic computation. So that's good. Now this slide is even one step more complicated, and I just want to so you can actually also, for general AdS space, you can calculate analytically this thing called the tree level 4-point contact term. meaning it's just this kind of diagram right here. You're looking at the 4-point function between 4 points here. And how this works is these objects here, this is a bulk to boundary propagator. So one of these objects is the propagator from this point on the boundary to a point in the bulk. And then this other one is this other point here. And so how this term is calculated is you see an integral here. So you take these 4 objects and you integrate over all the interior points. So this point in the center moves around all the points here like this, okay? And the discretized version of this is this line right here. So the only other thing I need to point out in this slide is this u variable here, but this u variable is defined as this object here. You might ask, what the heck is this? I'll just explain intuitively what this object is. Basically, if you fix 3 of these points here, like this one, and this one, now if you take this point, you start right here, and then you scan over this entire region of the boundary between this first point and this last point here, you will go over the entire domain of U here from 0 to 1, right? So this is what's known as in conformal field theory as a cross ratio. That's just an aside. It's why people look at this, but that's where this the domain comes from in here. So anyways, it's just analytically it's a non-trivial object, but if you do it on the lattice, you still get a good agreement here. So this is a pretty non-trivial check here, and yet the lattice still gives a good answer. Okay. Of course, we can also, do our due diligence when we're dealing with lattice. We have a finite volume. We can look at the finite volume corrections. How we typically do this is we just look at the it's called the low-lying eigenspectrum. We just look at the first, several eigenvalues and make sure the lattice theory, looks correct to the continuum theory. So you can actually solve for the continuum theory with a cutoff and then look at it versus the discretized lattice. And you find that, the low-lying eigenspectrum is very close, right? So all these eigenvalues, especially below 20, are almost bang on. Now, one thing I didn't mention earlier that is very common to do on a lattice is to refine it. And so the finite element method allows one in principle to converge to the exact solution just via refinement. So you could say, let's construct this lattice and let's just refine the heck out of it. Let's just make smaller and smaller triangles, and then we can, get better and better answers. And although that is certainly true, I'll just point out that when you do this refinement, so over here is a refined lattice, it's a little difficult to see, but when you do the refinement, you're actually breaking, you don't have pure equilateral triangles anymore. You no longer, you break the uniform regular tessellation of AdS space. And why that's bad is that when you're looking at the field theory side of things, since you've broken these inherent isometries of AdS space, then the type of operators that you can get on the QFT or CFT side, you start having to worry about counter terms to get rid of operators that shouldn't be there. So you broke some symmetries of the theory that you're trying to study, and so therefore more operators can be there that are annoying, that you don't want there, so then you have to worry about counter terms to get rid of them. So in principle, that's why we try to, as I said earlier, maintain this maximal discrete isometries of AdS space with the original tessellation. Nonetheless, you can refine it and ask what happens. And indeed, you can refine it. So the observable I have here is I've taken the center point and I'm just looking at its propagator to all the other points on the lattice here. And if I do this, just this one point to all the other points here, I get a pretty bad fit, 1.5 1.3. It should still be 1. I'm looking still at the case where this should be 1, the massless case. We refine it once, it gets a lot better, 1.08. We refine it twice, and yes, it gets very, very close to 1. Okay? However, there's this question I kind of alluded to, is refinement even needed? Again, when we refine, we break the isometries that we're hoping to preserve, so we really don't want to do that. So what these two slides are here, so this plot on the left, this is the previous slide here where we've just taken the lattice, we've refined it once, we've refined it twice, we fitted what the analytic, we fitted to what the analytic form of the bulk propagator should be to derive the fit here. Now, when I say the finite boundary condition over here, what I mean by this is that over here, this GBB that we solved for, this propagator that I showed the analytic form several slides back, that's solved for the case of AdS when it's, it goes off to infinity. Okay? So you can actually solve, it's not pretty, you can do it in Mathematica, and it can solve it technically, analytically, it's very nasty, but you can solve for the form of this propagator for the finite boundary condition, right? So instead of AdS going off to infinity, or in this Poincare disk model, infinity being at r equals 1, you can actually solve the continuum propagator for the case where instead of r equals 1, you're in a little bit, so you're at r equals 1 minus this epsilon cutoff. So you can actually solve for GBB in that case, and it's very nasty, but once you solve for it, then if you fit the lattice data to the true form that you're looking at, so you solve for the theory where the cutoff is the same as the boundary here of the lattice case, so now we're really comparing apples to apples, and then you fit to that, you find that even down here, delta original, which means that there is no refinement whatsoever, it is already very, very close to what the true answer should be. So 1.01 is much better than 1.29 with no lattice refinement. So no worrying about counter terms or anything like that. And that's actually quite remarkable. I think that just shows that, if you think carefully, these tessellations, again, they preserve this maximal discrete subgroup of AdS2. So you have the correct tessellation of the space you're wanting to look at, and you take care of the boundary conditions correctly, you can get very accurate answers with even a very small, a 3-layer lattice like this. There aren't that many points here, right? So we're trying to approximate an infinite space with this thing right here. So it's quite remarkable. Okay. So I just want to really point that out. Of course, you can, even with once you have the correct form and boundary conditions, you can then refine this lattice too. And I mean, you can really kind of nail down the answer you expect. But really, we don't want to do that. And I think this is evidence that we don't need to do that. Okay. All right, good. So I went over the 2-dimensional case in detail because it is central to the 3-dimensional case here. But before I do that, are there any questions on the previous section?
So you answered one of my questions because I was really curious how you were taking derivatives in this.
Yeah.
But one thing I was gonna ask, and this is more of like an implementation thing, and so if you're gonna talk about this later, or if you're using someone else's code, then I definitely don't expect you to do this. But I was really curious how like you implement this as a lattice, like for, you know, R4, all you have to do is like set up an array, basically.
Yeah.
But this is more complicated because you have more than 4 nearest neighbors.
Right. So there's two ways. One, actually, Dean Howarth, from RPI,
Yeah.
he had some code in C that created this, that can create lattices like this. It just starts off saying, okay, we have equilateral triangles. Let's just rotate them around the point and then flip them, rotate them around, construct the nearest neighbor table. Then we can construct that, that matrix, that quadratic form, And then we just need to invert that matrix, and boom, we're done. We have all the propagators. Okay.
Gotcha. No, that's interesting.
So that way is very nice, and that way scales up very nicely for large lattices. Now, there's another way that I did in
Who's
Mathematica.
asking this question? I can't figure it out.
Oh,
It's
Paul
Paul.
is.
It's Paul Martin.
Oh, thank you.
Yeah, so there's another way which is slower but is nice too. In Mathematica, I basically did it the group theory way, took the generators of the triangle group, acted in this coordinate system, and then you can see it just create the points layer by layer. Mathematica has a very nice built-in function to create a Delaney mesh. So it basically creates the lattice. It creates a few, there's a little bit of errors in there, but I can go through and get rid of them. And so that way is how I then created the lattice in Mathematica. And then also in Mathematica, then to get the refinement, you have to solve for the midpoints between the equilateral triangles and then solve for the geodesics between the midpoints to find the triangle lengths and stuff like that. And so I just did all that in Mathematica. So there's the very practical, quick way that scales up nicely, and then but you really can do it using this group theoretic approach. So we had two ways we did it, is I guess the answer.
Yeah, no, that's great. No, thank you. That's really interesting. And yeah, I'm in contact with Dean every now and again, but that's really interesting. Thank you, Cameron.
Yeah, definitely, no problem.
Maybe I should this is not a crazy lattice. Every point has 7 neighbors, right? So when you finally write a code, you can make a list of points, and then you can have a array that tells you how to get to the 7 neighbors. And so, these are sort of semi-regular lattices. In a sense, they're just as regular as a cubic lattice in that the geometric sense.
Right, it's regular. It's just that, I mean, like whenever you construct a lattice, you don't typically like store the nearest neighbors, right? You just each time you want to call it, you figure out what are the nearest neighbor points, but that wouldn't work for this.
That's right. So a general tessellation uses what's called a neighbor table. Okay.
Mhm.
But if the neighbors are equal in number, then that neighbor table can be mapped into an array. So I'm just saying that it's not as bad as you think.
Okay.
I
No,
mean,
that's great.
completely random lattice is bad because each neighbor is an unknown a list, and then you have to do something more complicated. It's called a forward star representation.
I see. Great. No, thank you.
There's systematic ways to do that.
Good, thanks, Rich.
But it's a very good question. You obviously want an efficient way, right?
Yeah. I will say that the C way is obviously, much more efficient. The Mathematica way was, thinking about the refinement, but because of this slide, we showed you could refine, and then we felt no need to really scale that up, put it into C or C++ code so we can run it really quickly. So it was a little redundant, but good check.
Yeah, no, thank you both.
Yeah. All right, so sorry.
Hi, sorry, can I ask a
Yeah.
quick question?
Of course.
So you showed a plot of the lattice 4-point function that you obtained and matched it to the curve.
Yes.
And it was somewhat lumpy in a regular sense. Is this
Yeah.
a lattice artifact?
Yeah, definitely. You mean this kind of lumpy
Yeah, because it
curve
looks
right here?
like kind of pure, like pattern looking.
Yeah, exactly. So it's from this so you can kind of these waves here are from simply the fact that we're looking at boundary points on this lattice, and I don't think I can zoom in, but like when you zoom in on these boundary points, they're not all at the same distance out from the center. They actually start to become, they're not even all like, excuse me, the more layers you go out, the more different sub layers at the boundary each of these points are, meaning, so for one layer right here, obviously all the boundary points are at the same distance away from the center. When you go out to a second layer, you actually have 2 different lengths that the boundary points could be at. When you go out to 3, there are 3 different lengths. And so as you start going, so for 8 lattice, there are, many different lengths that the boundary points are at. And actually, interestingly enough, the so-called boundary points, some of the so-called boundary points are closer to the origin than some non-boundary points, just because they've curved back in on themselves so much. So the boundary is like when you get way far out.
Look, but these are great questions, but
Yeah,
a regular
these
lattice
are,
is more lumpy than you think. People just ignore it. Look at
yeah,
the distances along the X and Y axis are equal distance. We'll go along any strange direction, and they're weird distances. So if you take a point in a square lattice and look at all the distances to all the points, it's very lumpy. So I mean, one of the things is people have ignored. This is not much worse. You see.
yeah. That's
Every
actually,
distance from the origin of a square lattice to all the other points, you'll find it very lumpy. It's called a lattice artifact. So this is not any worse than that.
I see. Thank you.
I mean, people just ignore the lattice oftentimes when they,
yeah, that's a great point, Rich. Yeah, no,
Yeah.
it's definitely true. Okay, good. So let's talk about the three-dimensional case here. So little d, is going to be 2. But yes, that's based on this paper down here, done with Rich and Evan Owen. Okay. So for the three-dimensional case, we're going to be using what's in the literature called the cylinder representation. So, on one of the first slides, I was talking about how we could have different coordinate systems of hyperbolic space or Euclidean AdS space, and one of them was global coordinate system where the boundary was this cylinder, this r cross s to the d minus 1. Really, it's just a cylinder. That's this right here. So really what we're going to do is we're going to take our two-dimensional case and then we're just going to add a linear time direction to it. So in this geometry, the bulk, the anti-de Sitter space, is now the interior of this cylinder, and the conformal boundary is the boundary of this cylinder. And time in this case, runs from bottom to top. Okay, right. And so recall that the metric for just hyperbolic space in general can be written in this form here. And this is nice because basically we split out the time component from the spatial component. And in fancy mathematical speak, you can say that the dilatation operator is the generator of time translations. All that means is that time runs linearly from bottom to top in this picture. So it's not some funny linear combination of different coordinates or something like that. Really, time evolution is separated out from the spatial component, and we can take care of it easily. Okay, right. And also, practically speaking, we've already tessellated the two-dimensional case. So we want to kind of use what we've done before. It's like the minimal effective dose. We want to just do what we've done before and do the easiest thing we can to just get to new physics. Okay. So in this case, when you're using this geometry, I said it in words, but we're going to be using global coordinate system, which is given by this metric right here. I do want to point out that the one difference compared to the Poincare disk model coordinate system that we were using in 2 dimensions is that rho now goes to infinity. Okay, so this is kind of like an infinite cylinder. Like so these boundaries really these boundaries are at infinity or conformal infinity is what people call it. So it's just slightly different. There's still rotational invariance at a time slice, but yes, rho goes from 0 to infinity. That's its domain. Okay, so going back through the process of solving the Bolt-Green's function equation, you actually find this very nice form in little d equals 2. So remember there was this nasty, I called it, the 2f1, this hypergeometric term multiplied by an exponential term. And it turns out that when you plug in to that equation many slides ago, little d equals 2, it collapses to this nice form here, this 1 minus exponential term here, which is kind of amusing. And in this case, the geodesic distance, sigma, is given by this equation here. All right. Okay, so let's go back through discretizing the action again. So we're also going to look at phi-4 theory in this case. So here it is again. So now we just have a time direction. That's the third direction in this case. So now when we do the discretization, we see something that looks very much like before. Whoops, these last two terms here. But now we have a time component out front here. Also, I'll point out that in this discretization or tessellation, we have this cosh rho factor now out front of everything. So there's this kind of warping factor out front. And we'll see what that does in a second. I'll just say that continuing this process, we could, of course, now discretize time. So time has not been discretized yet, but we could discretize it. And then we get something that we explicitly see is, we explicitly see in this term right here, this is the two-dimensional case multiplied by this cosh rho I factor. And then we have the time component over here, which is also inversely multiplied by this cosh rho I factor, okay? So there's a warping not only of the spatial component, but there's a warping of the time component, and they're inversely warped, so to speak. Okay, before proceeding, I'll just point out that we could, so at this step here, we haven't discretized time. We've discretized space, we have continuous time. We could have proceeded and written down a Hamiltonian form, right? So you can actually show that this is the Hamiltonian for this action right here, right? And this is good for studying, you know, if you eventually want to study with continuous time, dynamics, things like that. So, you know, you don't have to necessarily just discretize time. Okay, so let's look at some observables. So we're going to do things very much the same as before. At first, we're going to pick a time slice, so we're going to pick a constant time, and we're going to look at all the spatial propagators. Now, you might think, oh, this is just the same thing as before, you know, but again, going back here, there's now this this warping factor out front. So it's actually not, it's not the same propagator. So it is a new non-trivial check. So we expect, in this case, remember little d is 2, we expect delta to be 2 now. And if we do it, if we just, again, invert the matrix, we do a direct inversion here, we get, and we fit it, we get delta is 2.04 or 2.05, right? So there's a little more warping from, a little more lattice artifacts, but, you know, most of the points are out near the boundary, and actually it ends up being a pretty good fit. Of course, now since we have this other direction, we could pick a spatial slice and then look at the temporal propagator, meaning we just take the same spatial point and look at its propagator to itself in time. So we also expect that to be delta equals to 2. And if we do that with a direct inversion here, we get this fit right here. So around 2.2. So a little worse than the spatial case, but actually there's this, because of this cosh rho factor in the denominator down here, right here, as you go out towards the boundary, there is a massive amount of warping of the time component. So given that there's a huge amount of warping, it's actually pretty good. I should have mentioned at first that in the time direction, you know, we take periodic boundary conditions. It's a small aside. Of course, we could just do now all-to-all propagator, you know, why not? So let's just look at all points to all other points. So one point to all the other points, both in space and time. So this might be a mess, but I mean, it still is very linear. So yeah, you do a direct inversion, you fit it, and you get delta close to 2.2, and you get a nice linear looking fit over here. Good. Okay, so one more. For you could also do a radial propagator. So this is also, another non-trivial check. Don't want to get into the details actually of it, but you could pick a time slice and look at the radial propagator. So just take this point in the center and look at all the other points out here. And when you do a direct inversion of this, you get delta is 2.08. We also use this as a starting point to check our Monte Carlo, because eventually we're going to be doing numerical non-perturbative physics, non-massless case, where we actually have to do Monte Carlo. So this is a good check at first to make sure that the method works. And indeed, both the direct inversion and the Monte Carlo agree very well with the theoretical value. Okay, good. So now that we've done our due diligence, now we can actually calculate some new physics. So we asked, does phi 4 have a bulk critical point? Okay. Now, this is kind of a right. So now we're looking at the phi 4 action here, except now, we're going to make lambda non-zero, m non-zero. We're just looking at this full action here. It's unclear at first if we can even expect a bulk critical point. Okay, so there are a couple reasons why, and maybe some of them, you just have to take my word for, but AdS is famously an IR regulator. This is why people love to put things in AdS. It suppresses length scale, so it naturally acts as an IR regulator. Okay, and this means that if you take let's say you take a particle in AdS at the center of the universe, or the center of this tessellation, and once you kind of propagate out past the inherent length scale of AdS space, beyond this little script L that I was talking about earlier, the particle basically propagates without interactions. And it turns out, I did not explicitly say this, but the length of these equilateral triangles is around the AdS radius. So it's kind of puzzling. You think basically even from one point to its nearest neighbor, if you do the calculation, you would expect that the interactions are actually very weak. And so, of course, if you're looking for a bulk critical point where basically all the points somehow know about each other and come to this special critical point, critical behavior where they're all, you might not even think this is possible if in AdS space, these points can barely talk to each other. Okay, I know that was very intuitive, maybe confusing, but nonetheless, it is kind of non-trivial at first whether you can even expect a bulk critical point. Right. Okay, so that was AdS expresses length scale. Also, most of the points are on the boundary. So if we're looking at a bulk critical point and most of the points don't talk to, or only weakly maybe talk to each other, and most of the points anyways are on the boundary, which we're not looking at, then maybe you can't expect any sort of large scale behavior. Okay, but we're going to proceed ahead nonetheless. So the easiest thing to do here for our Monte Carlo calculations is to set lambda to 1 and to sweep over the mass. Okay. So if we do that and we look at the Bender cumulant, right? So the Bender cumulant is one of the tests for a phase transition. I believe you all have seen this over the past couple of weeks, but basically this variable here, when U4 is 0, it's in the disordered phase, and when U4 is 1, it's in the ordered phase. And so this transition, this step-like transition from 0 to 1 indicates this second order phase transition. And clearly, if you just look at the data, there is a very well-defined step function in the Bender cumulant. You can also look at the magnetic susceptibility, which is maybe more common observable to look at, is that, when you're at a critical point or second order phase transition, the magnetic susceptibility undergoes, there's a peak in the magnetic susceptibility. It technically diverges at the critical point, right? So again, with when you do the Monte Carlo and you look at different layer lattices, you can clearly see that there's this peak in the magnetic susceptibility as well. Okay, so there clearly is critical behavior going on. Right. So just putting these side by side, we clearly see evidence of a second order phase transition. Now, there's just a few caveats that I want to point out. So the scaling exponents in this case are not critical exponents, meaning these exponents right down here. So normally in flat space, which I believe some of you have worked on over the past couple weeks here, you can do a finite size scaling analysis and you can derive critical exponents, okay? So that formalism though, that's designed for uniform lattices in flat space, not these skewed or warped lattices in hyperbolic space. Not that you can't do it there, it's just that it's non-trivial and we basically, we need to think about how to do that more. There is no one's even attempted it. There's no formalism to do this yet in hyperbolic space. Okay, so that's one caveat. The second caveat is that further study is needed to classify the boundary CFT. So ideally, if you could, in flat space, you derive critical exponents using this finite scale analysis, and then you say, aha, these exponents mean this is part of the Ising universality class, or, things like that. You can characterize the theory. So because of this caveat here, we need to, there is a CFT, there has to be, there's definitely a bulk critical point. We can't say at the moment what type of, I'm sure it's in the Ising universality class, whether it's long range Ising or short range Ising or something in between, requires actually, the critical exponents are pretty close for all those. So you need to make sure you really nail down your analysis. But so we don't want to make a claim about which exact CFT class this is in. Okay, so that's kind of further study is needed in order to do that. Okay, this kind of segs into future directions here. All right, so future directions. So first, for the two-dimensional case, we didn't do this, but we could go back and study the 5-4 case at strong coupling, right? So we could go back to the two-dimensional case and do Monte Carlo there and really kind of look at the strong coupling case. And we could compare the CFT, what you get, the dual CFT1 spectrum, so we could compare what we get on the boundary, the operators we see there, to constraints from the conformal bootstrap, which you may have heard about, but it's just a technique, a way to constrain and identify basically the space of CFTs just using, purely mathematical arguments. You're just constraining it from the math of the CFT, to put it in colloquial terms. So that could be interesting, right? So I just mentioned this. The other thing we need to do is go back and to fully understand the approach to boundary in AdS3. And if we do that, then perhaps we could answer this question of whether the CFT there is a short or long range Ising model or something else. Oops. We could also, I had said that, and not only said, but written down the Hamiltonian for the case of AdS3, but you can also do it for AdS2. Yes? Or no? So what you can do is you could go back and look at the Hamiltonian version here, right? Then you could just Wick rotate, so you could just add an I essentially, excuse me. Sorry. So we could look at unitary time evolution for quantum computing. Basically, we could stick this on a quantum computer, right? So we have this Hamiltonian. We could Wick rotate it to put it in Minkowski space. We could then simulate it on a digital computer, normal computer with a Trotter expansion, but then we could, put it on an atom-based quantum computer, or just, simulate it with Qiskit and on IBM. There's a whole host of things we could do. We could just basically study it with a quantum computer, right? So maybe this is the beginning of a whole subfield of AdS quantum computing and error correcting. This is more of an aspirational goal. It's very difficult, but you could, of course, include, people are very interested in gravity, so you could include perturbative gravity by varying the lengths of the links, right? So when you do that, you're now inducing these fluctuations of the background space-time. And of course, we know from GR that there's this inherent, basically the geometry and basically the matter are one and the same thing or one and the same. And so basically by, adding fluctuations, by varying the links, you're creating, I'll call them gravitons, but you're creating perturbative gravity, right? And so what this means in CFT speak is that the CFT on the boundary will now have a stress tensor that just corresponds to the gravitons on the interior. But nonetheless, that's more of an aspirational goal. All right, that is all I had for today. So thank you for your time, and happy to answer any other questions.